All right, so what we have here is a standard maximization problem, and I'm going to talk about what makes it a standard problem. Our goal is to maximize a certain function. We call that function z, having to do with x and y, where x and y has to be somewhere in the region defined by these inequalities. And as you look over to the right, you notice that in Desmos there, I have the feasible region sketched. And remember the set of equations and inequalities we have to use in order to get that picture. Remember that I graph each line as an equation. That way we can find corner points if we have to. And then the purple here is the set of inequalities with the x greater than or equal to 0, y greater than or equal to 0 included. So what makes this a standard maximization problem? Well, think of a typical maximization problem. A maximization problem says you have available this set of inputs, okay? And your goal is to use those inputs in such a way to get the most out of it. So you're trying to basically make x and y together as big as possible so that you get the maximum out of it. And that big as possible, of course, is going to be probably one of these three corner points, right? It's not going to be 0, 0, because that's like the lowest of the low. And that's the whole nice thing about using positive coefficients. When all the coefficients are positive, you know that the solution is going to be one of those other corner points, okay? So we saw from before that the solution has to come from, like I said before, a corner point. So I'm going to use Desmos here to figure out what those corner points are. Now the red line here is 2x plus y equals 20. Just notice that the y-intercept of that line is up here at 0, 20. You can find that by letting x equal 0 when solving for y. And the x-intercept is 10, 0. Same idea, let y equal 0, solve for x. And you notice that 10, 0 is also a corner point. So I'm going to write that down over here. And 0, 0 is automatically a corner point, but it doesn't tell us a whole lot. Notice that this other corner point here looks like 0, 9, and it is, like I said, is the y-intercept of the blue line, which is 3x plus 7y equals 63. So that's not too surprising there. And then we get this other corner point where the lines themselves intersect, and that looks like 7, 6. And again, could have gotten that algebraically, but we're using Desmos to do that. So the goal is now, we plug in each of these points into the z function to figure out which one is the biggest. It is as simple as that. So if I plug in 10, 0 to this function, well, 10 times 10 is 100, 12 times 0 is 0. So that means the value of z is 100. If I do plug in 0, 0, it's more or less just a formality at this point. I am going to get 0. And like I said, not useful information. You're always going to get 0 for these things. If I plug in 0, 9, well, that means x equals 0, so 10 times 0 is 0. 12 times 9 is 108. So right now, that is the contender. That looks like the biggest, or the point that's going to give us the biggest. And then 7, 6, well, let's see. 10 times 7 is 70. 12 times 6 is 72. So that means the value of z is 142. Remember again, the point xy has to be somewhere inside of the region. Well, inside or as we see on the boundary of the region. So if I try to use any other point, like 7, 7 or something like that, it's going to be outside of the region. And that's not going to be a viable value for us. So the maximum value occurs at 7, 6. And the maximum value is 142. Now, once again, just to reiterate, this is a typical setup of a maximization problem. This feasible region that you see right here is a typical feasible region for a maximization problem, starting at 0, 0 and going up to a certain point. And that again is because we do have a highest that we can go for a maximization problem. Later on, we'll talk about a minimization problem and what those feasible regions tend to look like. So be sure to stay tuned for that one, and thank you for now for watching this video.